back to my channel. Today we're going to be looking at the Advanced Higher Chemistry 2017 paper. We're focusing on section 1, multiple choice. If you haven't already tried this, then pause the video now, try this part of the paper and come back to use this video to help you mark it. Question 1. This question has been designed to catch you out. All noble gases are characterised by the completion of the outermost orbital. If you look for the noble gases, they're in group 8, they're in the P block of the periodic table. This would immediately make you think that B will be your answer, P orbital, as the block that the elements are in is the last orbital to be filled. However, at the top of the noble gases is helium. The last orbital to be filled for a helium atom is an s orbital, not a p. So that means that our answer is in fact D. Question 2. The electronic configuration of an atom of X in its ground state is given. So if you add up the number of electrons that you have here, it's 21. We have an atom, not an ion, so that means this is the same as the atomic number. If you look up atomic number 21 on the periodic table, you will find that it is scandium. Which line in the table could represent the 4 quantum numbers of an outer electron in an Mg2+ ion? So if we start by writing out the electronic configuration for a magnesium atom, and then if we take off 2 electrons to make it an ion, we lose the 3s2. This means that our outermost electrons are in the 2p6. The 2 here is the energy shell, so D cannot be our answer. L is the next quantum number we're looking at and takes values from 0 up to n-1. So the 2 options are 0 and 1. S would be 0, P is 1. So that means that B cannot be our answer. The next value, M, is the directions that the orbitals take. And this goes from -L up to +L. So for us having an L of 1, we can have -1, 0 or +1. A is -2, we can't have that, so A is not the answer. S can always be a +0.5 or -0.5, so C is our answer to this question. Question 4. The coordination number of an ionic lattice can be determined by using the following equation. So it's a radius of the positive ion divided by the radius of the negative ion. So you need to look at page 17 of your data book to find ionic radius. For zinc it's 74, and for sulfide it's 184. If you take the ratio of the two, you'll find it's 0.4. This lies in this region here where we have a coordination number of 4, giving us an answer of B. Question 5. What is the formula for the diaqua tetrachlorocobaltate 2 ion? So we need to split this up into the different parts and see what we have. So diaqua means that we have 2 waters. Tetrachloro means we have 4 chlorines. Cobaltate, we have cobalt, and it's a 2+ ion that's being used here, but the 8 part means that the complex ion itself is negatively charged. So we need 2 waters, so we can immediately cancel out B and D as options, leaving us A and C. We want the number on the outside of the brackets to be negative, so our answer is A. Question 6. Which of the following indicators is most suitable to use in a titration of dilute hydrochloric acid and dilute ammonia? Dilute hydrochloric acid is a strong acid. Dilute ammonia is a weak base. This means that when you get to the end point of this reaction, your pH will be less than 7. You need to use page 20 of your databook and look up these indicators. You're looking for an indicator with a pH range that is less than 7. The indicator which is less than 7 on page 20 out of these 4 is C, methyl orange. Question 7. The pH of a solution of benzoic acid with concentration 0.01 moles per litre is what? So on page 4 you can find the equation that you'll need to use, which is pH equals a half pKa minus a half log C. This is because benzoic acid is a carboxylic acid and therefore a weak acid. To get pKa, you need to look at page 13 of your data book. You'll find that the pKa for benzoic acid is 4.2. If you put pKa into here, your concentration is 0.01, and if you do this calculation, you find that your pH is 3.1. So C. Question 8. A reaction must be exothermic if. So here we're looking at delta G, delta S. The equation that we're looking for is delta G equals delta H minus T delta S. If something is exothermic, the delta H will be negative. If we have a look at all of these options, a reaction has to be exothermic if delta G is negative and delta S is negative. So if we have a negative here and we have a negative here, these two will cancel out to make a positive number, but this can still end up being negative even if this is negative. If delta G is positive and delta S is positive, there is no way that this can be negative. Delta G on its own doesn't have an influence here on delta H, and delta S on its own wouldn't have an influence on delta H. So our answer is A. Question 9 requires you to do a little bit of calculation. So you've got a reaction A plus B to give you C. You've been given the following data from an experiment, and you've even been given the rate equation. You're trying to work out the value of X, which is this particular rate here. So to be able to work out rate, you have to have the concentration of B, which you have, but you don't know K. So your first step is to work out K. So I'm going to use the values from experiment 1 and put them into the rate equation. So the rate is 0.05. We don't know K yet, and we've got concentration of B squared. This means that K will be 5. If we now rewrite out this equation, so this time we're trying to work out rate, which is X, we know that K is 5, we know the concentration of B is 0.2, and we're having that squared, so this means that the rate itself is 0.2. So our answer to this question will be D. Question 10. Another rate question. So the rate equation for the reaction between nitrogen monoxide and chlorine is given, and we're trying to work out the units for the rate constant. So if we write this out again, we've got rate equals K, concentration of NO squared, and concentration of Cl2. I'm going to put a line down the middle here. All of the units on this side need to cancel with all of the units on this side. Rate is always in moles per litre per second. We don't know what K is yet. For your NO squared, you have moles squared per litre squared. It's just the units of concentration that have been squared. And then for the chlorine by itself, we have moles per litre. If we now cancel what we can on either side, so we have a mole here and a mole here, we have a per litre here and a per litre here. We've got nothing to cancel the S to minus 1, so that needs to just go over to the other side. And we need something to cancel this out, so we simply invert both of these. So we'll have mole to the minus 2 and then litre squared. So you're just inverting these units. That means that if you wanted to, you could now cancel all of the units down, and that means you have the right units for K. Now I've written them in slightly a strange order here, so you just need to find which one it is here, and it's D. Question 11, which of the following describes the bonding in ethane? So if we draw a quick sketch of ethane, 2 carbons, 6 hydrogens, all single bonds here. We have carbons which are sp3 hybridized. Okay, so we've got 4 sp3 hybrid orbitals there, which are forming sigma bonds only with all of the atoms. So this means that our answer is B. Question 12. Here we have pyridine, and we're to work out how many sigma bonds there are in the molecule of pyridine. So first of all, we need to fill in any atoms that are not being shown, since this is a skeletal structure. So all of the carbons should have 4 bonds, your nitrogen should have 3, which it does. So we've added in those hydrogens there. Now we need to highlight where we think our sigma bonds are. So every single bond is a sigma bond, so all of the ones to the hydrogens, these ones here, and then for every double bond there is 1 sigma involved. So if we now count those up, we have 1, 2, 3, 4, 5 to the hydrogens, and then 6, 7, 8, 9, 10, 11. So we have 11 sigma bonds within this pyridine structure. So this one here is just a definition that you need to learn. So racemic mixture, we looked at racemic mixtures when we looked at stereoisomers. There are 2 types of stereoisomers, geometric and optical. A racemic mixture is to do with the optical isomers. So we can immediately discount C and D and have a look at the other 2. So a racemic mixture is defined as A, a mixture of 2 enantiomers, or B, a pair of enantiomers mixed in equal proportions. It's B, they're mixed in equal proportions. Question 14, you've got 2 equations there, and you're to pick out the nucleophiles in the 2 equations. So first of all, we need to know what a nucleophile is. So a nucleophile is a reagent with a region of negative charge, or with a lone pair, which is attracted to a region of positive charge. So these are both nucleophilic substitution reactions that are going on here. So what we have happening is the NH3 is coming in and it's substituting for the Br, and the OH- is coming in and substituting for the Br here. So these are your 2 nucleophiles, so your answer is D. Question 15. A compound X has a GFM of less than 100. Complete combustion of X produces carbon dioxide and water only. Reduction of X produces a secondary alcohol. Which of these is compound X most likely to be? So step 1 would be to work out the GFM of each of these to see if we can eliminate any. So A has a GFM of 58, B has a GFM of 92.5, C has a GFM of 72, and D has a GFM of 120. So it can't be D, can immediately discount that. Complete combustion of compound X produces carbon dioxide and water only. So the only elements that you should see within a molecule to produce carbon dioxide and water only are carbon, hydrogen, and potentially oxygen. B has chlorine in it, so it can't be B. We're now down to A and C. Reduction of a compound X produces a secondary alcohol. So to get a secondary alcohol, we would be looking for a ketone. A is an aldehyde, so our answer is C. Question 16. We've got some information in the table about some amines and their boiling points. And then based on the information in the table, you need to identify which of the statements is true. Now all of the statements talk about primary, secondary and tertiary. So your first thing to do would be to identify which of these is primary, secondary and tertiary. Primary amines will only have 1 carbon group attached to them. Secondary amines will have 2 carbon groups attached to the nitrogen, and tertiary will have 3. So the first one in the table is tertiary, the second one is secondary, and the last one is primary. So let's have a look at each statement. So the tertiary amine has the highest boiling point. This is our tertiary amine, we can see it has the lowest boiling point. The secondary amine has the lowest boiling point. So the secondary amine is the one in the middle, you can see it does not have the lowest boiling point, the tertiary does. The primary amine has a lower boiling point than the tertiary amine. So here's your primary, you can see it's higher. The secondary amine has a lower boiling point than the primary. That one is true. So D is our answer. Question 17. Compound Y reacts with the product of its own oxidation to form an ester. So for all esters, you need an alcohol and a carboxylic acid. You can oxidize an alcohol to a carboxylic acid only if it's primary. Okay, so you need to have a primary alcohol to be able to oxidize to form a carboxylic acid and then react the two together. So propanol is an aldehyde, propanol is a primary alcohol, propantool is a secondary alcohol, so won't oxidize to a carboxylic acid, and propanoic acid is the carboxylic acid that would get used. So our answer is B, propan-1-ol. Which of the following statements about benzene is correct? Let's start by drawing a diagram of benzene. So benzene has 6 carbons and 6 hydrogens. Let's just add those in here. All of the carbons in a benzene are sp2 hybridized, so that means that they are planar with 3 bonds coming out here, and then above and below they have an unhybridized p orbital, which forms this ring of electrons here in the middle. So benzene molecule is planar, but let's just check the other 3 answers are not correct. Benzene does not react with electrophiles. Benzene has a lot of electrons here in the centre, so electrophiles will attack benzene quite easily. Benzene readily undergoes nucleophilic attack. It does not undergo nucleophilic attack since it reacts with electrophiles instead. The benzene molecule contains carbon-to-carbon bonds of 2 different lengths. If we'd drawn them as a double bond and a single bond, then yes, that would be 2 different lengths, but we know that they're actually all equal bond lengths and then have the ring of electrons. So our answer here is A. Question 19. Chlorine has 2 isotopes, 35 and 37. These isotopes are present in a sample of 111-trichloroethane. The number of molecular ion peaks expected in the mass spectrum of 111-trichloroethane is what? So your molecular ion is the highest mass ion and is based on what you have there in your sample. So there are different options for trichloroethane. Option 1 would be that all of the chlorines are 35. Option 2 is that all the chlorines are 37. Option 3 is that you've got 1 that is 35 and 2 that are 37. And then option 4 is that you have 1 that is 37 and 2 that are 35. So that gives you 4 options for the highest mass that you could see within this mass spec. So B is your answer. Question 20. The following substance was analysed using an infrared spectrometer. So for infrared, you're looking at page 14. The spectrum produced would not have a significant peak in the wave range of which. So if we take each of these in turn, so 1700 to 1680 is C double bond O, 2962 to 2853 is alkane, 3100 to 3000 is benzene, and 3500 to 3300 is an amine. So if we look at the structure, we have a C double bond O here, we have alkane single bonds to carbons throughout, we do not have a benzene ring, but we do have an amine. So our answer is C. This won't be seen in the spectrum. Antisense drugs are a group of medicines that act by binding to DNA to block the synthesis of some proteins. Which line in the table is correct for antisense drugs? Okay, so first of all, we're looking at classification. So it says here we're blocking synthesis, so we're stopping something from happening. So it's an antagonist, so it's A or B. And which receptor are we binding to? So we're binding to DNA, so it cannot be B, so our answer is A. Question 22. Which of the following would be most suitable as a reagent in the gravimetric analysis of silver ions? So for gravimetric analysis, you're often doing a precipitation reaction. So if we imagine we have a solution of silver ions and we need to precipitate those out, so you want to look at page 21 in the data book. Sodium nitrate would form silver nitrate, which is very soluble, so sodium nitrate wouldn't be useful. Potassium sulfate produces silver sulfate. Silver sulfate is soluble, so again, not useful. Barium carbonate itself is insoluble, so not useful for trying to do a precipitation reaction. And D, ammonium chloride, would produce silver chloride. Silver chloride is the classic one that we would use to precipitate out. So our answer is D. Using colorimetry, the most appropriate filter for determining the concentration of green nickel ions in solution would be what? So here you want to look on page 20 at the colour wheel. So green, if you have a look at green on the colour wheel, you want to look opposite green. So if you look opposite green, you will find that it's 380 to 400 nanometers. You just need to find which of these fits into that region, so it's A. Question 24. The diagram shows a thin layer chromatogram for a mixture of amino acids. Which of them has an RF value of approximately 0.75? So for RF values, so it's the distance the spot travels divided by the distance the solvent front travels. So looking at this, we're looking for something that goes approximately 3/4 of the way up as far as the solvent front. So it can't be amino acid P, it's not went high enough up. So it's between Q, R and S. So if we calculate each of those, so Q is at 6, the solvent front's at 8. So for Q it would be 0.75. And if you just check R and S, R is at about 0.85 and S is at about 0.94. So your answer is amino acid Q, which is C. Question 25. Which line in the table shows the properties of the most suitable solvent to extract caffeine from an aqueous solution of tea? So if you think about what you're trying to do here, you've made your solution of tea, which has caffeine within it. So you've made it in water. You're now trying to get the caffeine out of the water and into something else. So to do this, your caffeine needs to be more soluble in the other solvent if it's going to move into that solvent. So it can't be C or D. The solutions that you're using, you want to try and separate the caffeine away from the solution of tea that you've made. So it wouldn't be useful if the two solvents will actually mix together. So you need your solvents to be immiscible. So that leaves us with A as our answer. Question 26. A series of titrations was performed to determine the concentration of vitamin C in a brand of fruit juice. A standard solution of fruit juice was prepared and titrated with iodine. So an experiment that you've likely done in the past. Which of the following would be a suitable control? So a control experiment is where you do an experiment using the actual substance that you're trying to investigate. So if you're trying to look at vitamin C in fruit juice, your control experiment would be to repeat the same process using actual pure vitamin C so that you know that it works. So the answer here would be B. Question 27. You've got an equation here of a precipitation reaction, and you're given information about what was added together. So you've taken 50 centimetres cubed of 0.01 mole per litre barium hydroxide, and you've added it to 50 centimetres cubed of 0.01 sodium sulfate, and we're trying to work out the concentration of sodium hydroxide at the end. So to be able to work out the concentration of sodium hydroxide, we need to know moles and we need to know volume. We know volume because we've added 50 and 50, so we know it'll be 100 mils, which is 0.1, but we don't know how many moles of sodium hydroxide we'll have. So we can either work out the moles of hydroxide ions or the moles of sodium ions. Either of them would be appropriate. We'll work out the moles of hydroxide ions. So moles of hydroxide ions is going to be concentration times volume of barium hydroxide that we're using here. So that is the moles of barium hydroxide. For every mole of barium hydroxide, we have 2 moles of hydroxide ions. So we're going to multiply by 2. So we know how many moles of hydroxide ions there are. all of those hydroxide ions will now be in the solution of sodium hydroxide at the end. So if we do concentration equals moles divided by volume, our concentration of sodium hydroxide will be 0.01 B. Question 28. You have 1.06 times 10 to the minus 2 moles of phenylamine and you're reacting it with 5.16 grams of bromine. Which equation shows the correct stoichiometry? So you know how many moles of this you have, you know the mass of bromine, so we're going to work out the moles of bromine. So if you take 5.16 and you divide it by the gram formula mass of bromine, remember that bromine is Br2, you get 0.032 moles. So if we write that in the same notation as the other moles, I have 3.2 times 10 to the minus 2. So this is 3 times the moles of phenylamine, so our answer is C. Question 29. Ibuprofen is used for relief of pain, fever and inflammation. Structural formula for ibuprofen is shown here. If one tablet contains 300 milligrams of ibuprofen, how many tablets can be manufactured from 1 mole of ibuprofen? So we need to know what the mass of 1 mole of ibuprofen is. So the chemical formula for ibuprofen, if you count it up, is C13H18O2. So remember, when you're using skeletal formula, you can go in and add in the H's here so that you can see everything before you count it. So the GFM of ibuprofen is 206 grams. Now we're working in milligrams here, so if we times that by 1,000 to get that into milligrams, that'll be helpful. So each mole of ibuprofen weighs 206,000 milligrams. If we then divide that by how many milligrams there are in 1 tablet, that tells us we can make 687. All of these have been written in scientific notation, so 687 is 6.87 times 10 to the 2, so that's B. Lastly, question 30. The term accuracy is used to describe how close an experimental result is to the theoretical value. The term precision is used to describe how close a set of duplicate results are to each other. So you can be accurate and be close to an experimental value. You can be precise and close to the results that you get in your own experiment, but not be accurate. Or you can be accurate and precise, where your results are all close to each other and they're close to the actual value. So we've got 4 students that are determining the percentage by mass of chlorine in hydrated barium chloride. Which of the following sets of results is both accurate and precise? So the results need to be close to the actual value and they need to be close to each other. So A, you can see, are close to each other. B are not that close to each other. C is close to each other. And D is not that close to each other. So B and D are not precise, but A and C are. So what we need to do now is find out how accurate are they. So we need to work out the percentage by mass of chlorine in this hydrated barium chloride. So first of all, we need to get the GFM of this substance here. So it's 244.3. Percentage of chlorine in there is going to be the 2 chlorines, so 71, divided by the full GFM times by 100, so a National 5 calculation there, and that comes out to be 29.1. So A is the one which is most accurate. Thank you for watching my video. I hope that you found it helpful. Please remember to subscribe, follow me on Twitter @MissAdamsChem for regular updates on new videos. Bye for now!